Well, good morning again, and welcome to Plenary Session 2. As we resume this morning with the words from our speakers this morning, in particular Senator Kaine, I wanted to just mention ODU, Old Dominion University. You've heard their story this morning resonating throughout. One of the things that Old Dominion has done over the last couple months is do a strategic hire. Her name is Elsbeth McMahon, and she is leading Old Dominion University's maritime initiatives, strategic goals and objectives, and I thought it would be a good opportunity to introduce her to you now, and she will in turn introduce our next panel. So Elsbeth, thank you.
Thank you. Thank you, Ray, for that kind introduction. Good morning, distinguished guests, visitors, and attendees. Thank you for being here at Oceans 22 in beautiful Virginia Beach. As Ray mentioned, my name is Elsbeth McMahon. I am the new Associate Vice President for Maritime Initiatives at Old Dominion University. ODU is an anchor organization in a coordinated regional effort to ensure a thriving maritime ecosystem that not only benefits Hampton Roads, but the entire Commonwealth and beyond. We have vast resources and opportunities right here in our own backyard. We have one of the world's deepest natural harbors, the world's largest naval base and highest concentration of Navy vessels, the largest concentration of shipbuilding and ship repair activity in the country, a top port and logistics node, multiple commercial shipping and logistics headquarters, and developing industries in offshore wind and autonomous technologies. ODU is committed to growing the K-12 workforce pipeline for maritime skilled trades, which is a necessity in this region. We are also committed to strengthening industry outreach and expanding internships, co-ops, and networking opportunities for our students. Increasing interdisciplinary research, as ODU is an R1 university, promoting diversity, and providing the right curriculum and training for our students to have not only jobs, but careers that they can grow and succeed in. We are investing in vital programs such as cybersecurity, data science, mission engineering, advanced manufacturing, coastal resilience, and supply chain, logistics, and maritime operations. ODU also fosters entrepreneurship and innovation for startups and small businesses in the maritime space through Open Seas Technology Innovation Hub. This globally focused center that works with innovators, entrepreneurs, researchers, and industry to identify innovative solutions for problems in the maritime and coastal arenas, and helps to launch sustainable businesses and operations. With that being said, I'd like to introduce the Executive Director of Open Seas, Mr. Jerry Cronin, as the moderator for this panel for Oceans Technologies, Breakthroughs, Challenges, and Opportunities for Security and Stewardship. Thank you. Jerry?
Thank you, Elsbeth. I'm a storyteller, so I always coastal dwellers, right? Discovering there were tastier fish and shellfish a little bit offshore, but understanding over time that, oh my gosh, you get tired if you try to go out there for any long period of time. Till somebody comes up with the bright idea after an observation, hey, logs float, right? So a little log goes out there, you're able to stay there a while. Pretty soon folks are learning what's going on. Somebody comes up with the bright idea, hey, what if we tie them together? What if we hollow them out? And over time, a body of knowledge builds, and essentially technology is advancing the economy and the well-being of that tribe. And that then expresses itself in things like, the Phoenicians going all over the place, or Pacific Islanders, learning about the stars, currents, wave refraction patterns, and being able to make really long voyages, hitting small targets in the middle of a giant ocean. Another one, which is one of my favorite examples, is Sagres, Portugal, early 1400s, Prince Henry the Navigator, assembling, kind of like in this room, brightest in their field, cartographers, map makers, shipwrights, all those sorts of folks, and advancing science to the point and sharing lessons that instead of going a third down in the coast of Africa, all of a sudden they're going around, and then eventually, as I identify it as, it was the world's first global maritime innovation hub, because out of there launched the age of discovery and tying the whole world together. That all came through observation, sharing of knowledge, sharing of lessons learned, and aiming at going forward. And the result is the world is largely the way it is now because of maritime and ocean innovations. Big, huge part of it. Now advance a whole bunch of years. It's not over, as everybody in this world knows. We can do equivalent impacts and opportunities to grow the world further. We're concerned with things like decarbonization, minimizing impact on protected species, ocean plastics, increasing the efficiencies of commerce. I think Senator Kaine mentioned it, speeding up the development of ocean-based renewable resources without creating additional problems. It's a very slow process right now. We've been involved in it, and it's kind of interesting, and really, kind of improving life for everybody. On top of that, throw security concerns, illegal and underreported fishing, that sort of thing. Cyber attacks on shipping lines like Maersk, and sabotage of assets like the Nord Stream pipelines going into Europe. Those are all things that innovation, research-driven innovation can have an effect on. Over the past few weeks, I've been to a lot of conferences, done this type of thing, and just participated in some, and you're hearing that the opportunities are out there. International Trade Symposium, folks like CMA, CGM, and ONE, which are world's large ocean carriers, are asking for help. They want to be responsible stewards, but they're concerned about things like how do you get better situational awareness so you can make your routing better, which I think somebody hit earlier, or do science-based knowing where the North American right whales are, so instead of slowing down because they might be there, you're slowing down because they are there, which has a significant economic impact upon shipping. Last week or the week before, The Economist, the World Ocean Technology and Innovation Summit. A lot of money there. VCs and innovators looking for ways to pull projects together and looking for things to invest for the next, to take the world forward. And even things like NATO just finished a challenge around resilience issues, basically the recovery phase of an emergency. So there are, maritime is a target-rich environment right now, and this panel's put together to represent the spectrum of folks involved. We've got academia. We've got folks who are kind of both sides, which is the Navy, which are operators, but also do a significant amount of research. And we've got somebody from the industry who's going to be looking at what they're doing, but also the opportunities for interactions with each other. So what we're going to do is I'm going to introduce each person. They're going to do a few minutes. And then at the end of that period, we'll have some questions. We'll open up. We'll hopefully have a pretty good discussion. First on the agenda, Eric Terrell from Scripps Institution of Oceanography's Marine Physical Laboratory, one of the 4 original Navy University applied research laboratories established in World War II. 28 years of seagoing experience, both in basic and applied research, working with engineers, data analysts, and ocean scientists to conduct relevant research, actively involved in the development and application of new technologies. Received a lot of awards, has worked on a lot of different projects, and plus 34 years of diving and undersea experience. So I don't see the gills, but I imagine they're there somewhere. So over to you, sir.
All right, thank you. It's great to be here. Are my graphics up and running? Awesome. All right. Well, you might think I'm from the San Diego Tourist Visitors Group. I'm not. So my name's Eric Terrell. I'm an oceanographer at Scripps, and really proud to be able to represent the academic community on this panel. I guess show of hands, how many people here have been to school? All right. So I think I'm preaching to the choir a little bit here. So just bear with me here through my bad jokes. That's what you get for rain delays getting me into my bed around 3 a.m. So if we advance the slide here just really quickly, just wanted to really the underpinnings of a lot of our field is it's a discovery-based field. Development of new technology, some of the predecessors that the footsteps that we try to fill really have made all their ocean discoveries by developing new technology. Awesome. New technology, wireless. So with the development of these new tools, I think it's still fair to say that with development of a new widget going to sea, we make a new discovery, and then we have the underpinnings of the physics and the science and the STEM fields behind us to try to interpret those new measurements. I think it's really worth looking at history before we move forward, and these are just some historical photographs of programs that have taken place at Scripps. And one of the things I wanted to kind of lead off with is we're actually a celebratory, or there's an anniversary year right now. This 65 years ago, Sputnik was launched by the Russians and really changed for the U.S. how we were going to face education here from STEM-based fields. And I think probably all of us are somewhat of a product of, as a result of the U.S. realizing, guess what, we're getting behind. I would say a bottom line to some of what I'd like to speak to is I think we also need to keep having that sort of mentality that we might be falling behind and need to make those investments in the science and technology at the educational levels. These photographs that you see behind me here represent some of the very early days of ocean technology being developed. On the far left is the Deep Tow system, was actually a predecessor to a UUV, which actually, those systems actually found and detected hydrothermal vents and really changed our understanding of how the Earth system operated. You wouldn't think of it as a technology, but in 1946, a textbook, which actually was compiled of a set of notes by Harold Sverdrup and some of his colleagues, was called The Oceans, and it was actually considered classified for a whole number of years because of the interplay of ocean physics and National Navy needs. And in particular, Harold Sverdrup developed the science of ocean wave forecasting and had a very young graduate student, Walter Munk, that supported this effort. And those results of their science of forecasting of waves and tides, much like what Dr. Drake talked about for sea level and inundation studies, were actually used to help guide what fateful day Normandy would take place. And I want to acknowledge, I did see Mary Monk in the audience here, so Walter had a storied career supporting the Navy, doing quite a number of amazing things. So but now shifting gears here to a little bit of opportunities, and I don't really want to focus on a particular technology, but looking at what challenge areas we're facing. And the first I would say is, as was talked about earlier, the ocean is not a bathtub. Sea level rise is accelerating as we need to begin developing place-based solutions to sea level rise and inundation. I think if you go over to the exhibit hall, you would see many of these robots that are shown here. I wanted to speak to ocean observing, and not just the technologies, but what are we going to do with those data when we recover those systems or have those data telemetered back? And there's a whole science and field that's exploding right now in data analytics. For you educators out there, I do want to stress, it's not just machine learning and artificial intelligence. Let's work on the real intelligence first. Teach your students about covariance and statistics before you start rolling in the machine learning black box. These observing systems are now being used to give us better ideas of forecasting. This is the tough coastline that Tom referred to, where we begin developing resilient systems to deal with high storm waves. Tom addressed that really well. Something I've personally been involved in is, as we've learned over time, that our management practices that were maybe developed in the 30s, 40s, 50s, all the way through the formation of EPA, ocean dumping maybe wasn't such a great thing. And something I've personally been involved in is the use and application of robotic technologies of how do we explore the seabed and revisit some of these sites where essentially have been sight unseen, problem out of sight, out of mind, but it turns out there's a lot of problems. Southern California marine mammals experience the highest rate of cancer, and they have high levels of DDT in them, and what we're finding is that there were dump sites that might be introducing this compound into the food web. Likewise, robotics are now finding a role in bringing closure to past conflicts. There's over 80,000 missing in action, still missing, many of them in the Pacific and in the Atlantic Oceans, and the Defense POW MIA accounting agency is charged with finding and relocating those remains and bringing them back. It turns out losses in the ocean are actually the most preserved and can be found and detected with underwater robots. Last, I wanted to speak to IUU, that not as an opportunity, but this field of big data, the fusion of information across remote sensing platforms. And this image right here is work from an ONR program where looking at the Republic of Palau, looking at IUU taking place. The slower image is a picture showing 2 vessels actually exchanging fish illegally, and those vessels subsequently were tracked. There's whole wide fields now being developed looking at pattern of life and data analytics on marine traffic that we can take not only from national security interests, but into environmental and food security interests. So with that, I'd like to close and pass on my mic.
Super. Next up, Josh Weaver, who's a senior scientist for autonomy at Naval Surface Warfare Center in Panama City. Dr. Weaver's been a principal investigator on multiple unmanned systems projects that have focused on developing autonomy architectures, behaviors, world model tools, and perception algorithms. He also collaborates heavily with the international community, uncrewed maritime systems, key technology area lead for the Technical Cooperation Program, and has been in a multiple number of international exercises. Current areas of research is on long duration and fault-tolerant autonomy. So, sir, over to you.
Thanks. So it's great being here today. It's a pleasure serving up here with all these panel members. So as Jerry was mentioning, I've worked in the autonomy world for quite some time. I've always been interested in robotics. My wife obviously picks on me sometimes because since my kids were young, I would always like to watch them and see how they learn and expand their understanding and knowledge. And I kind of take that to what I do on my daily basis. Working with uncrewed maritime systems, uncrewed systems as a whole, I've been able to see a lot of advancements over the past couple of years, past decade or so, honestly. Whenever you look at some of the work Dr. Tom Drake was mentioning with ONR, some of the work that we've seen with the program offices, Mark 18, and with the different gliders that we have operating out there, there's a lot of experience and development that's going on in the autonomy world, trying to understand how we can get this data, how we can collect all this data, but then also advancing our capabilities in these robotic systems. One of the things I kind of like is seeing where autonomy is developing. But what I want to kind of focus on is where it's going now, what we're pushing towards the most. Like Jerry was mentioning just a moment ago, my experience, my interest area is a lot of the long duration autonomy and kind of seeing where we can push that. Taking autonomy that can go out into the environment and operate for hours upon hours, weeks upon weeks, months upon months. We do have systems that are already operating out there, like those gliders that are collecting data, but we're really trying to push also for this concept of long duration autonomy that can also replan, adjust, change its thought process while it's out there in the water. Again, like I said with my kids, watching and seeing how they adjust to the environment and use the new lessons that they're learning to be able to modify how they're reacting in that environment. So for this, I'm talking, operating 4 to 6 weeks at least, being able to replan in situ, look at these type of systems. And so we're pushing really hard and seeing that autonomy is really kind of moving that direction. To be able to see that we're not doing just simple missions with a sequential list of tasks, but actually autonomy that can sit there and go out in the environment and learn what's happening and be able to readjust what it wants to do. Using perception sensors that are being developed today, being able to use those systems as tools, not just simply react, not just take the data that tool is giving us and say, okay, well, I'm going to add this extra task, but use it to develop a better understanding of our environment. Something that could be used for looking at bathymetry and bottom type, looking at salinity and currents, and being able to use that information to build a better understanding, a better world model, and then a semantic reasoning behind all of that that can then be used to change the overall mission plan while we're out there. Now, a lot of that kind of goes more into the essence of how do we operate these systems? How do we learn with this? And so we can do more complex things. So a lot of the work that we're looking at has been moving beyond just making these vehicles, but also how we work with our teams, our collaborators. How we take these new sensing technologies and integrate them into our tools. How do we develop these world model pieces? But then also with this long duration autonomy, how do we handle the new environments that we're working with and the failures that we might come across? Like Dr. Tom Drake was mentioning earlier, resiliency is a big piece. Fault tolerance is a big piece. Being able to understand what kind of problems we're having in that environment and being able to adjust our plans accordingly. And so one of the things that we're also trying to see, and we've been seeing a little bit more, is the ability for a system and the autonomy that's on there to be able to change its function, change its behavior whenever something fails. So not just sit here, we're going to run a sequence of missions, or we might even have some autonomous plan that operates during the environment, but that when a system starts failing or starts degrading, we have a graceful degradation of capability. The actual system can then adjust its plan according to what we're looking at. And that's one of the big things we're trying to push for right now as well, is seeing these autonomy solutions being able to take those sensors, be able to understand whenever the sensor's not operating like it wants, and we start pushing that behavior to adjust the overall plan. Whenever you're looking at a 2 or 3 day mission that's being run, you take into account the fact that the left sensor isn't operating as well, and so you shift the autonomy to account for that. Or more than anything, that you just don't abort. Or a lot of our autonomy right now, since it's the short duration concepts, they just abort and cry home, or ask for an operator to come help them. And so what we really want to do is start pushing and seeing more of that cognitive concept come into the autonomy, the cognitive architecture of how an operator thinks, how we think through making plans or adjusting to changes in our vehicle capabilities. We work with a lot of operators, and a lot of them you can see that they adjust what they're trying to do in that environment. And we want our autonomy to start being able to do that. We really want to start pushing for the autonomy to think through this process, deduct or deduce and infer based off of what we're seeing what we can change our capability to. The way that we do as people, as humans. We sit here and we look and deduce based off of all this information that's coming in, what our next step should be. And so we really want to start seeing that kind of creep back into the autonomy world. Instead of just making things bridging the gap between automation and autonomy, really start seeing some of those decisions being made on the vehicle instead of always having to call back to the operator and see how the operator works. Last thing that I kind of want to mention, though, is that with all of that, one of the big pieces that we have to understand, we have to push forward, is trust. Trust, verification, validation. You probably heard that banged so many times. We talk about it often, year after year. But there's a lot more focus, a lot more progress being made on that today. You'll see some of it being discussed during some of the sessions that are going on over the next couple of days, people talking about new frameworks, new ways of verifying and validating autonomy capabilities. And so we really want to see some of that work going on. The program offices, PMS 4.6 is pushing for that. We've got integration labs that look at trying to take these different capabilities and be able to demonstrate them. And so that way, when we do want to try to run a mission for 4 to 6 weeks, we know that that mission can do its thing, that we know that we can trust that it's capable of doing that. And so these program offices are creating these labs to be able to pull these capabilities together. We're creating metrics that allow us to take all this information and be able to say we can actually create a cost to this new function, this new capability that's coming out. And then finally, you have big frameworks like I talked about earlier, you're going to see talked about during these sessions that take each of these individual capabilities, their costs, their functions, and pull them together so now we have a good analysis of what we're looking at. We have a more mathematical principle, mathematical background of saying there is a bounds to the capability of the system. We understand it, we know that it can meet these accomplishments or these needs, and we can see all the interactions between the categories of capabilities or just interactions between sequential capabilities. And so there's a lot of this movement that we have, but it's going to take a lot of collaboration between all of us. I mean, like Jerry was saying up here, we have multiple groups up here. With us up here, we've got industry, we've got academia, we've got military, and it's going to take a lot more collaboration between each of us because now all these technologies are advancing. They're getting to that point where we can dovetail them together and kind of see how we can combine them and make this dream of a full-fledged autonomy that can run on its own for weeks upon time come to truth. So that's it.
Thanks, Josh. Next up, Tori Cobb. Dr. Cobb's a program officer at ONR and also the Naval Surface Warfare Panama City Division, a senior technologist for advanced signal processing and automation in mine warfare. Since 2001, he's been a researcher there, which is pretty impressive, and was a senior scientist assigned to the Advanced Signal Processing and ATR branch, serving as principal investigator on a number of items. Current role at ONR, he seeks to improve underwater unmanned systems perception by conducting fundamental and applied research in machine learning, sensing, and signal image processing. So, Doctor, over to you.
Thank you, Jerry. It's on? Okay. Good morning, everybody. It's good to be back at Oceans in person and see a lot of people that I haven't seen in a while. Like Jerry mentioned, I've been working in this area for a while, and in some of my earlier days in the early 2000s, I was at ocean conferences presenting papers on machine learning for side-scan sonar, synthetic aperture sonar, and some of those folks are still here today, so it's good to see those folks back. I think my introduction will be a bit narrow, but I think it's something that I have had passion for, still have passion for. But I think it's also, it's interesting from time to time to look back and to see how far we've come and kind of put a mark in the sand and say, hey, you know, this is what we've accomplished, but also to talk about what's next or what should be next. You'll see that I have a slide here to show you a few things, and I think most folks know what these things are, but the upper right there is a side scan sonar image from a fairly inexpensive side scan, and it just kind of shows you the complexity of the seafloor and the problem in finding objects in reverberation limited environments where you've got something that has a fairly low contrast in intensity with respect to its seabed environment, right? So we've got a lot of problems with clutter, we've got problems with motion with the vehicle itself, and those all manifest themselves in the image. And the bottom image is a synthetic aperture sonar image that was provided by Jim Prater, who will give a talk later this week in one of the technical sessions. And that's actually an image of fish pits created by a certain kind of fish that burrow into the sand. It produces kind of a time-dependent variation on the seafloor that can cause some difficulties in this problem. And then the right there are some sand ripples to show other kinds of environmental conditions we deal with. And so, you know, what's the kind of the problem that I've been working on for my career, and is a problem that's important to the Navy, is finding objects on the seafloor, right, with high accuracy, so we don't want to miss anything, but to do it very quickly, we have to minimize our ability to find false positives, right? And so we have all kinds of environments, we have all kinds of different sea states we deal with. This problem, I think, the advances we've made using unmanned systems has been pretty remarkable, especially within probably the last 5 to 6 years. Currently, you know, I think our sensors are really good. I think we have the ability to find fairly small objects. We have high-resolution sensors. These sensors are in the commercial world. You know, companies make very high-resolution SAS products that just 10 or 15 years ago they definitely wouldn't have been as good as they are today. So we've made a lot of progress in 20 years in terms of our sensing. Recently, through the development and maturation of those sensors, we've been able to collect some fairly large data sets that support these new deep network architecture designs for machine learning. And so through those advances, we've really reduced our false positive rate and made these systems more useful, right? You know, the days when the data came back and you ran your machine learning algorithms on the data and your entire screen was full of false positives that were kind of absurd to a human operator, I think those are pretty much over for some of our moderate to easy environments. And so I think this is a really big sea change, especially when we talk about triggering things like autonomy, like Josh is mentioning, right? So those low-level machine learning tasks are, you know, we're making progress. The other thing is, you know, through the advancements in GPUs, the miniaturization of these things, the reduction in power. We're actually able to embed this kind of stuff on unmanned systems. So we're providing more capability for our unmanned systems to find objects on board, right, to enable other kinds of behaviors and more sophisticated behaviors that can take place at the vehicle level. So this is another really important advancement. And so given that, I think some of the issues that we've resolved through these years in terms of processing speed, if we have enough training samples, can we get good results from our machine learning algorithms that are robust? Yes, I think to some degree. And our sensors are performing well. So what's next? This is some research we have in progress, some research that I support as a program officer at ONR, or through other programs I see that folks are working on at ONR or other places. In terms of, like I said before, if we have enough training samples, do we perform well using deep network architectures? I think the answer is yes. And the ubiquity of the software is pretty clear. You can download it off the internet. It's a pretty formulaic way to use these systems. But the research, I think, is in how do we get that level of performance with less samples, right? Josh talked about learning like a person or a child. You can show a child a crayon drawing of an apple, right? And then they can go in the supermarket and find it for you, right? You couldn't do that with a deep network system, right? So how do we get that level of performance from a human in terms of learning onto these systems? Because a lot of times for our problem sets, we may not have thousands of samples of an object before we need to go and find that thing on the seafloor. Another thing we should incorporate is things like causality. In terms of there was some work in Bayesian networks in the past that's now being incorporated into some of our deep network architectures that will cause kind of influences, cause and effect, versus just correlation. Right? We measure correlation really well with deep networks, but not causation. So this is another important thing, to understand what's the cause of something in order to predict it. Right? And robustness to adversarial attack, that's a constant issue as well. How robust are these networks? Can you inject things into either the sensing, the environment itself, or through the sensor to attack them, and how do we resist those attacks? I think the forefront of sensing is, now that we have really good sensors, now that we're getting better machine learning, how do we more tightly couple that into the autonomy of the vehicle so that our sensing and the feedback between our sensing and our prediction and our movement of the vehicle are more tightly coupled? I think this is a really interesting area. In land and air robots, it's a lot easier to do this. I think because they have the data to support this in an earlier time frame. I think we're still catching up for the undersea world. We're continuing to push the envelope in terms of high fidelity SAS processing. So we have really highly resolved seafloor. Now we're pushing it into 3 dimensions. We're pushing it into much smaller resolutions. And so there's still a lot to gain there. And then finally, this idea of what do we do with our data, right? I've heard in the preliminary talks this morning, we were talking about data, aggregating data, data scarcity, right? How do we, as a Navy or a nation, depending on our problem set, how do we employ all of those sensors we have out there and aggregate it in a way that we can exploit it to our advantage, either financial advantage, advantage of our ecosystem goals, or our military advantage. This is a really hard problem, and it requires a lot of coordination, especially at the government level, if we're trying to work this. But in order to really employ these tools, to employ the data science tools Eric mentioned, to employ advanced machine learning, or to really gain to gain that military advantage over it, it's going to take a coordinated effort. Once we do that, I think we'll really see another sea change and improvement of our algorithm development over time. So I'll close there, Jerry.
Thanks. And last but certainly not least, James Fisher, who's a Deputy Geotechnical Manager at Fouguereau Center of Excellence, located right here in downtown Norfolk. So it's good to have them here. He's got over 14 years of professional experience with marine infrastructure projects involving geoscience and geotechnical engineering. And just looking, it spans every industry you'd want to think of offshore: oil and gas, wind, transportation infrastructure at the global level. The only continent I don't see on the list of places you've done stuff is Antarctica, but given time, I'm sure you'll end up down there. So he's led these projects: site characterizations, site investigations, hazard assessments, model development, and geological studies. So over to you, sir.
Thank you very much, Jerry, and it's great to see you all. I have to admit the last 2 years I haven't got out too much, so it's really great to be here, and thank all the other panelists. It was really great. I guess I'm lucky to go last because I think I'll be deriving a little bit from each of your inputs. But yeah, I work for Frugro. If you know about Frugro, we are a global company. We do all sorts of things related to the marine environment. I'm going to touch on some of the things that I think I'm most excited about with technological advances. And so, let me advance here. And so, again, to touch on this topic of remote or autonomous, there it is. We do think it is the future, and we're actively working towards it now. We have things that we deploy around the globe, remote operation centers, which we refer to as ROCs, with the idea that we have staff manning these offices 24/7. Data is continually coming in for survey work or processing of data, and we're able to make real-time decisions based on that, as well as give clients the option to review their data in near real time. So it's pretty exciting stuff. A lot of this is being done in the Gulf of Mexico. We have a remote operating center in Houston, several in Europe, the Middle East, India, Australia, and Singapore, to name just a few. And so what we're also trying to do is work towards a fleet of uncrewed surface vessels, USVs. Part of that is benefits to the client. There's reduced risks, HSC incidents and things of that nature, as well as reduced carbon footprint. So, these are goals that we're actively working towards. And so we have successfully done several projects related to ROV dives, up to 400 hours from these, working from these remote operation centers. And we're working towards having some of this be autonomous work as well. So that is pretty exciting stuff. For some of the vessels, like with the image here of the Blue Essence, these are, purposely designed, of course, uncrewed vessels that are meant to work in more weather-tolerant conditions. Think of the nearshore environment. I focus on offshore wind, and we're anxiously waiting to get the opportunity to use these vehicles. But part of the issue or the challenge is with that is making sure that there is safe. There's a fishing community out there that we have to consider as well, and all the other ocean users. So even though these have some of the latest technology and detection, whether it's 360 cameras or infrared sensors, there's still, we have to work through those challenges of making sure that all ocean users with these uncrewed vessels out there, that everyone's going to be safe. But, I'm excited at the opportunities on the horizon, and I think they're coming soon in U.S. waters. So in my zone of expertise, I guess, it's related to geoconsultancy, working with data and making decisions on that. And I do think we've made some really good strides in Frugro with being able to take a client's need, whether it's schedule related and getting a quicker turnaround time or higher data quality in challenging environments for some of these offshore wind farm projects. So some of the images that I've shown here, at the top left is our RAM system, so our rapid aerial multi-sensor, aerial LiDAR mapping here. And so this is quite nice for problem areas or in the nearshore environment where it's difficult to get a vessel in. We've had several instances where we've used this where there's been shallow shoals, say offshore Massachusetts, where it's just not safe to get a vessel in there. Operating, so we've actually flown these RAMS missions to get a good, really high-resolution bathymetric data set. Some of these shoals could actually have sand waves that come out of the water or with only a few meters depth. So it's really hard to do a geophysical survey over such features. But with RAMS, we can get a very high-resolution image. I think in the project we did it last, we were up to 50 centimeters resolution of objects on the seabed in a bathymetric sense. So that was really great to work with. And then beyond that too, maybe at an earlier stage, getting this idea of what's on the seabed and how it's changing, using satellite imagery. Of course, there's a lot of great companies out there that are using this technology, and of course, so are we. Working there to derive what the actual seabed looks like and how it's changing over time. So a nice example there at the bottom right-hand corner, again, offshore Massachusetts, in a very challenging, highly dynamic environment where even in a year that seabed's going to change, where there might be a shoal, all it takes is one good nor'easter or hurricane, and it's maybe moved tens of meters away. And so how do you work with that? How do you make decisions? How do you predict where it's going to be? So using the satellite recon technology, we can actually go through, have our geoscientists either map that out individually or also with AI technology as well, which is what the other two panels are meant to illustrate. Now, I want you to picture this image for a minute. I want you to picture all of Hampton Roads, and then I want you to take 1 million volleyballs and just throw them. So if you picture that volleyball to be a boulder, glacial erratic, and you have to put cables through that area, but if you hit one of them, it could damage your installation equipment, and you have to pay millions of dollars to fix it. But that's our objective, is to all over Hampton Roads map these volleyballs. Imagine if you have 10 million of them, how long it's going to take an individual geoscientist to say, oh, there's a boulder, get all of its measurements, and go on to the next one. I would dare say that's well over a year. We've developed some in-house, AI technology, artificial intelligence, and as well as utilize some that's on the market from Esri, and just fantastic results. Mapping them might take a team of geoscientists over a year, as I said, to do. I think we mapped 8 million boulders offshore Massachusetts for one project alone within 2 months, and that was with also geoscientists going through to check, is it really a boulder or is it a fishing trap or something like that? So that was quite remarkable. And again, it's a need. We don't want an offshore wind developer who's going to go out and pay someone to install these cables to all of a sudden run into a boulder, and then you'll have a pretty big change order on your hands. So really great use of the technology that we have these days. So pretty exciting stuff. And it goes beyond that, mapping sand waves as well, which are important because if they migrate in with the ocean currents moving around, predicting how they're going to migrate, what their depth is. So that also goes in part for cable installation. Yes. So we kind of touched on acquisition, in-house processing, but the last part is the data, and somebody else already mentioned that. While it's just a massive amount of data that is acquired for some of these offshore wind farm projects, I think the latest one we're doing is up to 20 terabytes of data just for one single project. And that's bigger than a lot of our network servers used to be back in the day. So for one project, we have to take this massive amount of data, which could be multi-beam echosite or side scan sonar, magnetometer data, seismic data, and not only do we have to store it and use it, we have to be able to pass that along to the client. So it's also a challenge for them, which is really what this slide is meant to show. We're seeing huge amounts of data volume. You have to work with this data and share it with other stakeholders, people that are interested in cables or design of the monopiles or environmental groups. They all need access to it, archaeological investigations. So you need a way to manage it, to send it back and forth, to share it, and to use it. And so we work quite a bit with what we call a Gaia Hub. And so again, this is a cloud-based, even a GIS enterprise type platform. And we call it an engagement platform because that's really what it is. From a simple website, a user can go on there, have access to all this data. We have web maps to display the data, so if they want to see, what's the latest bathymetry from a vessel, they can go there, look at this web-based map, review the data, whether you're interested in cables, archaeological resources, benthic, or just geotechnical engineering. So they're all able to share this one resource, and really it helps a lot with making timely decisions. A lot of these projects are just dynamic and on the fly. You might get a cable layout one day, and within the next month, it's completely changed. And so how do you make these decisions faster, also to make sure you're capturing all the data you need? So using this, online geodata management system has been really effective that we found when working with our clients. And I really think that's all I have. So again, thanks, Jerry. This was a real pleasure.
Thank you very much. I've got a number of questions here that I'm kind of interested in. Plus, we've got some microphones in the middle of the floor. for folks who might want to join in. And I'm just going to start with a riff on data. And when I'm working with folks, I always say you can buy a topographic map for any place in the United States. I can get really good soil stuff from USDA to the point if I walked across this stage, it would tell me I had this different type of soil over here and this different type of soil there. Do you see us getting there for the ocean? And how do we overcome that whole, there's sort of these walled garden business models that people are building where my data, I've got it, you can redo it when you do it further, versus sort of that open data community. Where do you see that all going? And Eric, I'll toss that over to you.
I didn't tee up that question. So one of the hats I've worn in my past life is being involved with big data associated with the ocean. And one of the things I like to say is you can make a career out of going to data management meetings, and it's for those of you that are data managers, God bless you, you're doing the Lord's work. But you're really into the weeds many times, and I like to approach it from like a mission-driven perspective, that from what do we want the end result to be, so we're not just creating the Indiana Jones locker of data being stored somewhere that can never be accessed, but what outcomes do we want to have out of those data? How do we create federated data sets that can be tapped into? From the perspective, of course, the sensing of things above the ocean are so much easier than beneath the ocean. But I would say we're making a lot of progress looking at the academic community. David Sandwell, one of my colleagues, I think is at the forefront of creating bathymetry maps globally. Those maps get adopted into Google Earth, which is probably the public view of what is beneath the seafloor. But in terms of your underwater maps, one of the things I would comment is it's a whole lot easier to know what's happening at a bathymetric level at very high fidelity within U.S. waters than any other country's waters. I don't know if that's good or bad for the country, but I think it's a healthy conversation to say about how much information do we really want to broadcast within our 200-mile EEZ.
Okay. Anybody else want to chime in? Sure,
I'll chime in. I have a lot to say, but who knows if it's useful. But, well, first of all, a couple of thoughts. So, machine learning, like I talked about briefly, I talked about ubiquity of software. AI/ML is really in a kind of a practitioner stage or an engineering stage. 20 years ago, you used to have to read a textbook and understand a lot of how algorithms worked, program your own code. So today, a lot of the work is automated in machine learning. There's a lot of libraries folks can access. There's kind of a practitioner field. Companies have moved from what we call model-centric, which is making your own model based on certain data, really kind of handcrafted algorithms, to data-centric, where the specific models that folks use are less important than the data you have. Since we can exploit large-scale data with enough labeled data, the differences between the models is fairly small. And so really the model for industry to make money is to create a data vertical, right? So that you own all the code and all of the data, because the data is where the money is, right? That's how you can monetize that asset. So that's one way to look at a data vertical. Another way to kind of think of a data silo or data vertical to me is the legacy problem we have, which is closet full of hard drives, right? Or one-off experiment that ONR or NOAA funded and collected a bunch of data, and then 10 years later, no one knows where the data is, or the person retired, or whatever, right? And so that data has lost value. So you've got one problem is lack of access because someone is intentionally preventing you because there's some proprietary or monetary reason. The other is really kind of a change over time in how we store data or how we access it. So that's a problem, right? So how do, from a government perspective, how do I make the Navy better at a certain task by, exploiting this data? I think first of all, you need to create a kind of a place where we can store the data that folks can access, right? It needs to be stored in a way that is well documented and curated. I think at ONR, amongst my peer group, we're realizing this is an issue, and there are folks, especially in the basic research sides, that do a pretty good job of taking their data and putting it onto government-sponsored sites that do a good job of labeling and curating basic data. We've got to get a lot better at doing that with our data that's probably a little more sensitive, right? And then exposing that user group, so exposing our data vertical to a large group of people that can help us solve our problem, right? So those are some things that we're working on that we need to continue working on. And then I think in the last part, I think to really kind of, turn the key, or to make it really, to kind of, really increase the scale of the data we could gain access to, is to really create within the Navy or within government itself the same thought process, I guess within DoD itself, that they have at NASA, where the point of the experiment, or the point of the mission, is to collect data. The data is the point, right? So now we're getting to the point where we have lots of sensors out there. We have lots of ways to collect data. We have to treat the data not as an afterthought, as something we put on a hard drive and put in a closet and then go do the next thing. But the data is the reason we're doing the mission or the experiment in the first place. And so we need to have a plan and a long-term view for how we store that data and how we continue to exploit it and add it to a larger group.
Hello? Oh, there we are. Over to you, James, industry standpoint.
Yeah, no, and it's quite interesting what you're saying there. I've even seen in my industry the evolution where usually it was just a report. What are your findings? That's a bygone era. Anybody's going to say, well, we want the data as well. That way we have access to it. Some private developer for offshore wind. But I also have seen a lot of, on another side of the coin, a lot of what we might do is, desktop studies. Somebody's interested in an area. Hey, what background information you can find? And I can tell you, as recently, I worked on offshore California, some of the wind developments, lease areas there. At first, it was a bit of a bear, because you had to, go to the USGS websites, and then, okay, what's at BOEM, what's at NOAA, and you just, but after a while, what I started to realize is there was more this effort to kind of collate its central agencies, these data, at least in the Pacific Northwest specifically. I found some valuable portals that had a lot of the information that individual websites had in there. So it'd be nice to see that, go a step further, like I said, with more data available, but also trying to get one source of information out there, because right now you could spend a lot of time going to several different agencies, entities, academia, trying to find all the information you need. But I guess my message is I see a lot of hope and a lot of progress that it's actually going that way. So I'm looking forward to the times where we do have more of this open source access to the information that we all want to actively use on a regular basis.
Okay, I'm going to toss one over to Josh, unless you got something to add here.
I was just going to add real fast. One of the things would help with the data side of things is also understanding and knowing how people are going to use it. Obviously, training sets for ATR and sensing, that's a benefit. But what I was talking about earlier with the concept of the world model, making sure that we're telling people how we're going to be able to use this data, so that way they know what kind of data that we're trying to collect. And so we can start categorizing that and getting that type of information out to everybody. So.
Cool. So another one back to you. You mentioned trust in autonomous systems, and my ears perked up because we did a project with Italy Center for Maritime Research and Experimentation year before last on particularly that topic. What do you see as being the biggest issue in trusting those autonomous systems?
Especially, it depends on where you're at. So on the international scale, there's a lot of trust issues. So one of the big things coming out of NATO and CMRE, so they are working on trying to figure out how to task multiple architectures from a center location. So some centralized system sends out and tasks multiple vehicles from different nations. We even had a trial this past year, just a couple months ago, over in Portugal, where we were demonstrating the idea of being able to task these different systems. But that means that you're putting trust in two different directions. You're putting trust in the fact that the vehicle can accomplish the task that it says it can. And then you're also putting trust in the centralized system that's telling those vehicles what to do. There's a lot of work that's kind of going on in that part, not just in the sense of how you task all these systems, but being able to believe that when you say a vehicle is capable of accomplishing a task, that those who are operating the overall mission can do that. And it has been an open discussion. With working with the UK a lot, one of the biggest questions always came up is the US ever going to trust another nation to drive our vehicles? Or are we ever going to trust other nations' vehicles and their capabilities to do what we're asking them to do? So I don't know if there's an easy answer to that question. It is something that I think that the push that we keep going down towards trying to improve ways that we establish what a system's capable of doing, that we categorize what those functions are, that we can actually define the capability in a measurable mindset, something that again has a mathematical principle behind it, that we can then show bounds and show, hey, this is what this is able to do. We've demonstrated it's able to do that. And then when we come together on the international or even local stage, we can show all those functions, those capabilities. I think that's going to be a key piece for trying to improve that trust.
Thanks. And I see we have a question on the floor. Go, sir.
Is this on? Okay. Dr. Weaver started getting towards a little bit of my question. With what Dr. Cobb said, actually, the world has been great at putting tools out on GitHub and code and everything, but I'm reminded of someone once told me that it's easier for me to teach a computer scientist basic oceanography than it is to teach an oceanographer advanced computer science. And so with that in mind, one, do you agree with that? Two, how do we bridge that gap? And are your agencies or companies involved at all with student innovation challenges or anything to that like?
It's to me? Okay, sure. Well, I'm not going to choose, who's the better, transfer knowledge type oceanographer or computer scientist. They have their strengths and weaknesses. To me, I've only been, 20 years sounds like a long time. There's folks in here who's worked in these areas much longer than me. But in my mind, there's a few initiatives that really kind of drove this ability to transfer knowledge from the computer science world. And one of them was the OpenAI initiative. Taking research code, packaging it, and making it available to folks has really kind of changed the face of who can use these AI/ML tools. And so I would say with a working knowledge of Python, which by the way is the #1 IEEE Spectrum language of the year, last month or this month, with some knowledge of Python, which is taught in high school now. My sophomore daughter's taking this in high school. And access to some of these libraries, the use of the tools is fairly easy to get a hold of these tools and use them, right? Do you necessarily know what's happening under the hood? No, not necessarily. That takes a lot more work and understanding and practice and training. But I think the ability to use tools, the kind of tools that are out there for curated data sets is it's probably much easier for an oceanographer to use that than to teach a computer scientist oceanography. That would be my guess. There was another question kind of rolled up in there in terms of initiatives. At ONR, from my perspective, I work in kind of a naval warfare area, right? And, it's kind of world of finding objects on the seafloor. But I do see machine learning across other oceanography disciplines, and there's going to be some talks today. I think Dr. Briner's got some talks on clustering, some sound speed profiles. There's cross-pollination occurring right now in a lot of these areas. I think there's robust groups that work together with computer scientists or engineers that know how to use machine learning models and they know how to marry the science. So I think the pollination's occurring, and I'm happy to take that offline and discuss any other particulars.
So what I'll add is I agree with Tori on a lot of that stuff. I mean, the open source community as a whole has really improved that function, that the ability for us to start sharing knowledge and understanding across multiple domains. So I was talking about earlier with collaboration. I mean, it's a key piece between all of us to be able to work together. With the advent of the robot operating system, back before that a little bit, with the Mission-Oriented Operating Suite, or MOOS, these were a lot of the tools that a lot of the robotics community started working with and first really starting to share capabilities amongst each other. And with those type of pieces, we've been able to see those who are not computer scientists being able to take sensors and capabilities that others have developed and be able to tie their own sensors and capabilities to that. And then the developers of robotic systems can now take advantage of that. Now, of course, working in the military environments, we don't always get to public release and open source our code. But there is a lot of that community that still works back and forth with each other, even on the military side or the Navy side. And so that's kind of one of the key pieces that we'd like to see, especially with students. So we do try to reach out, of course, with ONR and through other groups where a lot of universities are funded, internships are handled, where we bring a lot of people in, and we do try to cross-pollinate a lot with those internships. We work with students from different domains, and we try to teach them the other domains. One of the key pieces that we have in our department where I work is that under robotics, it is a multi-domain disciplinary environment. But that's not just engineering, that's not just like computer and mechanical engineering. It's also data science, mathematics. It's really all of this knowledge and kind of coming together. And so we try our best to make sure that our tools and documentation that goes with that and the stuff that we're sharing out there helps everybody else kind of bring up to speed whenever it comes down to that knowledge.
Cool. We're almost out of time, so what I'd like to do is a quick lightning round so we can get a kind of quick hit from all the folks up here. Right now, in your opinion, like 20 seconds, what's the biggest opportunity out there? What's the biggest nut that hasn't been cracked, that if I was a venture capitalist or I was the government trying to figure out what I'd put money into that was high value, what would it be? James.
Of course, you have to start with the geoscientist. All right. Well, you know, I do think the one point that you brought up with your first question, you know, I would love to see, you know, more of this open mapping of the oceans, for sure.
Okay. Tori.
Since it's not my money, I would say zero or few shot learning. So the ability to improve our performance with less training.
Honestly, seconding that in a lot of ways, perception is a key piece. Being able to understand our environment as quickly as possible with very little data to back it up.
I don't want to give away all my good ideas. If there's venture capitalists here, see me at lunch. But one of the things we're missing right now, I think, as a community is we've got a technology sector, again, God bless you, a lot of inflation at TRL, and creating an environment where we can actually get lots of muscle reps with the technology to mature it, and there's no substitute for being in the ocean. So how do we create environments that allow for that kind of unimpeded experimentation?
Fantastic. And we've got 56 seconds left. I'd like to close it and thank our panelists. The ocean's always been an exciting place to me, full of opportunities, and I see great things going forward. So thank you for your time. Thanks.